I did some experiments this evening, and my first idea was let me make a sine wave oscillator with this type of coil. And it is a common coil, by the way. It's namely a coil that can transport audio, and of course in such a way that there is no DC coupling, because here we have a winding and here we have a winding. It's specially made for the audio band. They are very cheap, as far as I know €1 or so. And well, my idea was, let me make with this coil an oscillator, simple sine wave oscillator, but I could get a proper sine wave. But the more interesting things are to tell now. I made a kind of very simple one transistor organ with it. There are many circuits of these organs on the World Wide Web, and in old radio magazines of the 1970s, 1980s, 1960s. But I think my idea is in a certain way somewhat better, because I had good results. And this is the schematic. This transformer, audio transformer for microphones, etc., is now made into oscillation with one transistor. And the frequency is set with the help of this audio band switch, and you can turn the frequency with the 50 kilo ohm potentiometer. Of course, you have to set the oscillation first, otherwise it doesn't work. And the reason is here. This potmeter, 22 kilo ohm or 25 kilo ohm, sets the oscillation. So you hear a sound in the audio range. Important to tell that when it does not oscillate, reverse the windings here, these two windings. In such a transformer, there's always a top of the winding and say the ground of the winding. When it doesn't oscillate, reverse one of the two electrodes. Anyway, so what's this all about? It's an oscillator, but my idea is that it works quite nice, because the waveforms can be set. You can smoothen them out a little bit with the help of this capacitor. That is absolutely not necessary. And the good thing of the sharp pulses is that they give harmonics, and that means that there is a relation to certain musical instruments. For instance, a piano sounds different compared to a flute or a violin on a certain audio, certain frequency. That has to do with the harmonics. Each musical instrument has its own audio spectrum. So let me first show that it works. Perhaps that's interesting. Here I only have one hand, by the way. That is the oscillation. I have to put down the camera for a while, because otherwise I cannot give a demonstration about how the circuit works. I have to bridge, say, the button switch that is responsible for the attack. So now it oscillates. And on the scope you can see there is an enormous voltage and there is an enormous peak here on this frequency, and that also means that we have harmonics, and I've told more about that earlier. Anyway, So let's see what it can bring. Sound is quite fierce. Anyway, when I turn the pot meter here, and that also depends on, say, the rotary switch via which you can search for certain audio bands. Well, I want to give a demonstration that it is usable as a musical instrument. But first I want to demonstrate the decay here. When you add voltage here via the button switch and you charge a capacitor, the circuit will work for a certain time, and then when the button switch is going to the upper position, the circuit does no longer receive voltage, but the voltage slowly decays out because of that capacitor here, 470 microfarad. I'm going to demo it now. Here is that cap. So when I add voltage, and perhaps a good idea to show more how does this work together with the button switch, and the green one here is the button switch. So how does it work? This is the effect, and on the scope we have this. And well, I'm absolutely sure that this is, say, a kind of a strange sound that does not have to do something with music, perhaps, but I want to demo that also. I remove now the attack and decay capacitor, so that we have here this, and I want to play Bach. Sorry, Mr. Bach, that I've used your music, and want to, say, get in a certain touch with that Bach music. And of course that will be very difficult, but I'm absolutely sure that when you, say, make this circuit and, say, get experience with it, that it can help you in a kind of musical way. So anyway, I play Bach. So the music is kind of sleepers awake. You hear it on the background, and I will try to follow Bach's music with this, say, fool's organ. Let's try. Etc, etc. Well, this is, say, the mode where I use the button switch. But let me try to give another demo of this fool's organ. I think it is an interesting circuit that could be elaborated much further. So now a constant sound. I switched here the frequency band switch. Well, it is exactly, and that's a lucky shot, exactly between the two frequencies where this musical part works. When I turn it, hope it's visible. Anyway, so I think this is enough. Like I say, I have to switch off Bach again. A little bit disturbing. Thanks, Johann Sebastian Bach, for this demo. Anyway, I think it was a little bit convincing what I've done. Well, more explanation about the schematic. Attack and decay, you've heard it. When you switch on the oscillator constantly, I've also demonstrated it here, the attack and decay. With a big value capacitor, it is slow and the frequency goes down. Anyway, it's a fool's organ, kind of serious fool's organ. Well, that was more or less all to tell. Thanks for watching. Let's finally look at the waveforms. That is, well, that is perhaps again interesting. There are on the coil enormous pulses. And that with enormous I mean high voltage pulses. So, and these are, say, the different frequencies. And with that electrolytic you get this. Anyway, I have to put down the camera for a while to switch on to another frequency band. So, this is, say, the highest frequency band here. And turn the potmeter again, frequency potentiometer. That's interesting to tell. On a certain moment the waveform changes substantially into another waveform with less harmonics. So the sound gets more smooth. You can change that. Here it is a square wave, here set the position, and here we have, say, the beginning of a sawtooth wave. Anyway, I think it is an interesting experimental circuit that can be developed much further when you are interested in, say, music. Thanks for watching.